Okay, thank you so much. First of all, I would like to thank the organizers for their efforts to hold this meeting and inviting me to speak about my recent result on Stieltjes constant. So first the question in my presentation is what are Stieltjes constant? They appear actually in Laurent expansion of Dirichlet L series at S equal 1. They are here. And in this expansion, we should distinguish two cases. The first case when Dirichlet character is a principal, modulo 1, so delta chi here is equal 1. Otherwise, should be 0. So we don't have this term in S. Chi is not a principal character. In the first case, when Dirichlet character is a principal, the Laurent expansion of zeta function at S equal 1 is given by this formula, and gamma n here is our Laurent Stieltjes constant. And this constant actually can be represented at the limit of the difference between this summation and this term. And this term. Stieltjes was the first who gave us this definition of gamma n. For this reason, we called today this coefficient Stieltjes constant. After his definition, many mathematicians were interested to give a new proof of this this formula. Found also estimate for this constant, and maybe more interesting is to give the free region or study the free region of zeta function in the critical strip. In particular case, when n equals 0, so we are speaking now about the first coefficient. It is Euler constant, and as we know, gamma 0 in this case defined by this limit. And as most of us knows that there are many famous unsolved problems about the nature of gamma 0. For example, most famous one is this coefficient is irrational or not. In the second case, when Dirichlet character is not a principal, Laurent expansion of L function at S equal 1 is given in this formula, and our coefficient, I mean Stieltjes coefficient are here, are the value of the n derivative of L function at S equal 1. So here we can see, I use the same definition, but actually gamma n chi, we mean it is the n derivative of L function at S equal 1. So here we have an important formula, and this formula shows us that the study of n derivative of L function at S equal 1 is closely related to that Laurent Stieltjes constant for arithmetic progressions. And here just the same definition for this coefficient, of course, in arithmetic progressions. So what we should just mention here that many mathematicians tend to study gamma n AQ instead of gamma n chi, since they are less complicated to define than the n derivative of L function at S equal 1. So this formula totally is important to study the n derivative of L function. So the second question in our presentation is where we can use Laurent Stieltjes constant, and maybe what is the motivation to study this coefficient. So I just choose some points. Let's say Laurent Stieltjes constant allow us to compute Riemann and Hurwitz zeta functions in complex plane. Also determines the zero-free region of zeta function, as I mentioned before, in a critical strip. And if we speak about the first derivative when Dirichlet character is not principal, I mean L1 chi, so it helps us to study the class number of the quadratic field. So that's why we are interested in this coefficient. Therefore, the studies mostly focused on growth and sign changes of the sequence gamma n, explicit upper estimates for the absolute value of gamma n, asymptotic expressions for gamma n, and the numerical evaluation of gamma n2. So in this presentation, I focus on upper bound of this coefficient. And the first result in this direction has been given by Brinks in 1955. Here, his result, he gave us upper and lower bound of absolute value of gamma n by using his asymptotic expression of gamma n. And in the same paper, he could study the sign of gamma n, and he proved that there are infinitely many n for which gamma n is positive and infinitely many n for which that gamma n is negative. And later in 1972, Bernard gave us improvement of Brink's result. Here it is. Another result about this coefficient in terms of Bernoulli numbers has been given by Israelov in 1981. Here it is. And in special case, he deduced here this asymptotic expression for gamma 0. By using this formula, he could or he deduced the upper bound of gamma n over n factorial. Here it is, and as you see, we have here some coefficient related to k, and this one again related with complicated multiple summation here. For this reason, this term we cannot calculate it easily, let's say that for n, for large value of n. So as you see here for k1, 2, 3, fine, but after that we should estimate, say, k again. So in 1985, Matsuoka produced an excellent asymptotic expression for gamma n over n factorial, as you see here. He used to prove this formula or this equation, the functional equation of zeta function plus the Cauchy theorem. It's a classical way when we want to study such problem. In special value, when a in his integral here equal n over logarithm n and n greater than or equal 10, he got the best upper bound for the absolute value of gamma n. And this result actually had been the best upper bound for absolute value gamma n for more than 25 years. And many authors later tried to improve his result. One of them, Adil, in 2011, he gave us this upper bound for gamma n for any n greater than or equal 4, and he deduced from this one that when n goes to infinity, the absolute value of, the upper bound of gamma n is here. And as you see, the main term here appeared again, as we saw in Matsuoka result. We have exponential n log n, but still this term is much bigger than what we have here. So for this reason, still in that time, Matsuoka result is the best, let's say that. So the third question we can ask it, what about the numerical evaluation of gamma n? So what we can say about the numerical part of gamma n? Actually, this problem has been addressed by a number of the authors. But I should say that at the moment, the value of gamma n are not known precisely, and each author gives different value of gamma n. Although this value are close, they are still different. So the idea is to compute a large number of digits of gamma n for larger values of n. So at the beginning, if we want to go back, at the beginning, some authors used this formula to calculate or to evaluate gamma n, and it's worth mentioning that this equation is a slowly conversion. So it doesn't help when n large. For this reason, we can get it some value, the first constant of gamma n, but not for n large. Other authors also used another way to give some to study, the numerical or to make the numerical computation of gamma n. Maybe I should stop in a Kremenski result or computation in 2002. Actually, he computed the first 3,200 constant, and in his paper, he expressed gamma n as a limit of a more rapidly conversion sequence than this one here. And his method produced high precision than has been obtained to date. Later, Knessel and Kofi in 2010 compute the first 35,000 constant, and very nice series representations for the first two constants have been given by Kofi in his paper in 2014, and really nice result in this paper. He got it in this paper. Yes. Here maybe we can see some numerical computation of gamma n given by Kremenski and Knessel and Kofi in 2010. So you can just compare both of them, almost similar. Here maybe with more digits. Yes. Now, what about Laurent-Stieltjes? So we spoke about Laurent-Stieltjes constant for zeta function. And what about this constant for the Dirichlet function? So for the first constant, when n equals 0, I mean L1 chi, as you know, Dirichlet produced finite expansions for L1k. It is here. And always we should distinguish two cases. The first one, if Dirichlet character is even, the second, if it is odd. So, and similar finite expansion for other derivative form of L function at s equal 1 given by many authors. Here we have the names. Of course, I couldn't write everything because the formula a bit long and need more maybe notations. But as I mentioned at the beginning, this is one of the most important result or relation. And we can notice, and many authors used this formula to study, to give information, to study gamma and AQ, to get information about gamma and Q. So in this direction of research, I found two upper bounds for the n derivative of L function. The first one, we don't have a lot of upper bounds. So I found two results. The first one is given by Chiyotomi in 1994. So here, as you see, we have upper bound for n derivative of L function at s equal 1. This in the case we have chi is real, non-principal character modulo Q, and Q is cube-free. For Q goes to infinity, he deduces this upper bound for this coefficient. So most of nice result about Laurent Stieltjes constant for Dirichlet L function is given by Ishikawa in 2001. I think he is a student of Matsuoka because in his paper he used the same method of Matsuoka. He used the functional equation of L function and Cauchy theorem to deduce first his expansion of gamma n q chi, and then he studied this formula to get the upper bound for these coefficients. And here we have this nice upper bound for our coefficients. Yes, so now we have goal to find improvement of Ishikawa and Matsuoka result. In 2013, I wanted to study this coefficients again and try to give upper bound for them, and maybe we can get improvement of previous results. So here, as you see, I got this upper bound for general case, gamma n chi over n factorial. Chi here is primitive Dirichlet character modulo Q, and the Q we have between 1 and this term. Yes, maybe at the beginning you see it's a bit complicated formula, but if we take the special case when chi is a principal, for example, so we have improvement of Matsuoka result. Here I just want to show you by numerical way that our result is much better than the previous one. And by this result, we can say we have, let's say, an excellent upper bound for these coefficients in both cases, in L functions and for zeta function. So just maybe I should mention my method to prove this result. At the beginning, I used as Matsuoka and Ishikawa did in their paper. So I got this asymptotic expansion of gamma n. And then, as if you just have a look, sorry, it is here. Yes, here, as you see, it is in complex plane. So my idea was to improve, to move from complex plane to to real plane, and that I did that by using Mellon transform, and then by so careful calculation and computation, etc. I got my result here. Yes, here. This one. So the second, or I don't know what is the number, maybe the fourth question in my presentation is if we can use the same method for other zeta function. It's a natural question now to ask to apply our method for another zeta function. My idea was to do that for Dedekind zeta function, and it was a surprise to me when I didn't find any information, let's say, or very less information about the Laurent-Stieltjes constant for Dedekind zeta function. Actually, most information were about the first constant is called Kronecker constant. Most result about this constant because it is related with logarithmic derivative of L function. So we have many papers about this constant, but not for other constant. For this reason, I wanted at the beginning to study the sign of the Stieltjes constant for Dedekind zeta function, and I got this result, and it is now published. I don't want to stop here because also we need more notation, and I think 30 minutes is not enough. But just I want to mention what I got it in this direction of research. So, and in that time I was in Japan, and as I said, I was wondering why we don't have any information about other coefficient for Dedekind zeta function. And my colleagues from Shuta from Nagoya University and Checha from Kyushu University were excited to study together these coefficients again for Dedekind zeta function. And we got a so nice result about it. And after that, we decided, okay, we will not submit this result. We want to investigate this coefficient for more general L function. At the beginning, we considered functions in Selberg class, but later we discovered we can also extend it to class larger than Selberg class. So before showing you our result, I just want to remind you that Dirichlet series LS attached to arithmetic function f belongs to Selberg class if it is absolutely convergent when real part of s greater than 1 and satisfies 4 conditions. The first one, Ramanujan hypothesis, second, analytic continuation, functional equation, and the last one, Euler product. So this is Selberg class. And as I said, we can extend it, this class, and actually just we discovered that we can ignore 2 conditions. The first one, Ramanujan hypothesis, sorry, and the last one is Euler product. And in this case, we got the extended Selberg class S slash. So, and our function now LS, if satisfies just the condition 2 and 3, so it belongs belong to extended Selberg class. So now we defined our class, and let's define also Laurent-Stieltjes constant of L series when they are in extended Selberg class. So here we can see our Laurent expansion of LS, and here are the generalized Laurent-Stieltjes constant of L series. So, and now our result is here. As you see, we have many definitions, just don't look to these few lines. So the more important red line here, as you see, we can get the upper bound for our coefficient. And this is actually a generalization of many known results. So we have many definitions here about the degree of L and many things. So I don't want really to speak a lot about it. Just in this presentation, I want to show you that now we have more information about Laurent Stieltjes constant in general L functions, and maybe included many functions. And yes, so if you like to have a look on this paper, it is open access on Ramadan Journal, and here it is, the title also. And this is the title, my paper about explicit upper bounds for Stieltjes constant, what I showed you before. So this is what I want to speak about it. I think I finished on time. Yeah, thank you so much for your attention.